Hello students, welcome back to the next lecture on classical electrodynamics, and today's lecture number is 17, and today we are going to enter into the magnetostatics, and the main purpose of the today's class will be to understand the magnetic field in terms of some kind of potential. So the idea would be clear if you have understood the electrostatics part that we have been discussing in over the last few lectures. The point that we understand after solving the problems, for example, is that understanding the electric field will be more comfortable if you know the electric potential. So that means a knowledge about the potential would be more comfortable than learning the knowledge about the electric field. So that is what we understand from the electrostatic case. I'm talking about the advantage of having a potential. This is what we say the potential formulation. So the question is quite clear, why electric potential or why the potential formulation is considered advantageous when compared to the electric field itself. In the case of the electrostatics, it's quite simple and straightforward that the electric potential is a scalar quantity, whereas electric field is a vector quantity. So a vector quantity in three dimension means three scalars are involved, whereas the electric potential in the static field case, the potential is a single number. It's a single value, and therefore it's a scalar. So the point is that mathematically speaking, dealing with electric potential is going to be much more comfortable than dealing with the electric field as a vector quantity. So that was the reason why the potential formulation is considered more elegant. And one more thing is that in the case of the electrodynamics, that means when you are moving from the static case, you can't have a simple potential like gradient of phi. We say that the electric field equal to the negative of the gradient of the potential. That will not work when you are moving to the dynamic case. So there is going to be some extra term, but however there is going to be a potential. Okay, so the point to be noted is that electric field cannot be written down as the negative gradient of a scalar potential in case of dynamics. But we will see what will happen. There will be some additional term will be entering into picture. Anyway, that we will see later. So keep this point in mind. And now what we are going to do in today's class is in similar analogy, that in the similar exploration, if you want to do a mathematical analysis and understand the magnetic field, so the question naturally comes, for the case of the magnetic field also, can we understand or can we exploit the possibility of having a potential rather than a field? So that is a general interest, or that we have a theoretical reasoning like that. So we are not discussing in terms of practical approach. So that's a quite different story. In practice, that means when you are going to perform experiments or laboratory measurements, dealing with the magnetic field is more comfortable. You don't require a potential for that. And even when you are going to have a theoretical potential for magnetic field, we are not going to measure that directly. So when it comes to measurements and when it comes to practice, for example, we don't require the potential formulation. So the potential formulation of the electric and magnetic fields are in general very useful only in theoretical formulation. That means if you want to understand certain things theoretically, that means mathematically. Okay, we are asking the question on the mathematical foundations of the electromagnetic theory. When you want to understand the electric and magnetic fields and electromagnetic fields in dynamic case, the potential formulation is going to be useful mathematical tool for the general understanding of the electromagnetic theory. But when it comes to practice, we are going to perform measurements with magnetic field, not the potential. Okay. In the case of the electric field, of course, there was a possibility, and therefore we always measure the electric potential difference. So remember potential difference once again, not the exact potential. You can't measure absolute electric potential using any device. What all you measure using voltmeter is only potential difference. That means difference between two absolute potentials. So this is true even in the case of the gravitational potential, because electric potential and gravitational potential behave similarly mathematically. and therefore you can't measure the absolute gravitational potential at any given point. What all you can do is you can measure the difference between two absolute potentials. So this is the general situation. And coming to the magnetism, that means when you're talking about the magnetic field, especially static magnetic field, we are going to see that there exists a potential. So which means that mathematically we can understand the magnetic field in terms of a potential. That is the conclusion that we are going to have. But before that conclusion, we'll have to work out the requisite mathematics. And what is required as a background knowledge is the standard vector calculus, the Gauss divergence theorem, Stokes theorem, and then some of the product rules in vector calculus. That's all what is required for doing this. And we will now go into detail. We'll start with the experimental evidence of the magnetic field, namely the Biot-Savart law. So you should remember one thing, that in the case of the electrostatic also we started with the Coulomb's law. It is only the Coulomb's law which is an experimental observation. We try to understand them, and then you first understand that the field varies like 1 over r square in terms of magnitude, and later you discover the direction as a function of space, and then you try to formulate it mathematically. So the same thing that we apply even for this case, namely experimentally people have found out that a current carrying conductor has a field around it. In the sense, how do you know the field is around it is you can have a campus. Campus means you have a small magnetic needle where you have one side north and other side south. So the small needle will deflect when you take it near to the current carrying conductor. So therefore there is an interest is coming why it is deflecting when we take it near to the electrical conductor, or we say that current carrying conductor. Current carrying conductor is important. So that is how the interest has arisen experimentally, and people have found out what are the directions in which this compass is showing as you move near to the current carrying conductor. So that has given rise to an appropriate vector form of the equation, what we call the Biot-Savart law. So therefore the starting point for the today's class would be writing down the vector form of the Biot-Savart law. That's the first point. And of course the basic requirements would be the knowledge about the current density, and then the uniform motion of the current density. That is what is required for magnetostatics. Current density and charge density, how are they related? Of course you know it, but at least we need to refresh for 1 second that the current density is given by the charge density multiplied by velocity. So it is quite simple. You have a charge density, right, which are not at all moving. Charge density means a collection of charges distributed in space. So if you have a collection of charges are there in one place, then you allow it to move, or you move it uniformly. That means you move it with a uniform speed. Then we say that charge density is moving with uniform speed. So this English sentence is there, right? Charge density moving with uniform speed. That much sentence, you call it by a name, current density. So that's all about it. So current density is nothing but a moving charge density, and the movement has to be uniform. That is very important requirement for the magnetostatics. Okay, magnetostatic means static magnetic field. That means magnetic field will not vary with time. That will happen only if the charge density is not fluctuating. So when the charge density is moving, the density itself should not fluctuate. Fluctuate means number of charges should increase, decrease. Such kind of thing should not happen. If you are going to consider 1000 charges, or same 1000 charges should move without any changes in its number or in its position. That configuration that you start with, right, the initial 1000 charges, the same thing as such you have to move it uniformly. You should not redistribute the charge configuration. You should not add any charge, remove any charge. Then we say that the uniform charge density is moving uniformly, and in such a situation we say that the magnetic field is uniform and the study is magnetostatics. And of course naturally the charge density can move inside a wire. If you have wire, the charges can move, right? In a one-dimensional wire you can have one-dimensional current. Suppose if the charge density is moving in a sheet of aluminum paper, for example, aluminum foil, you can have a charge density it can move uniformly on a sheet of paper, conducting sheet. Then you'll have surface charge density, or correspondingly you'll have surface current density. And similarly, if you are going to have a very thick conductor where you can calculate its volume, then when the charge density is moving inside a very thick conductor, electrical conductor, then the current density will be correspondingly termed as the volume charge density and the volume current density. So you have two words. One is the volume charge density. When the volume charge density is moving inside the volume, then the current is known as volume current density. But there is a tricky point to be noted. If you look into the dimensions, the dimension very important. Volume current density, you believe that it is supposed to be ampere per meter cube, because volume, right? So ampere is there for current divided by meter cube, so that it is known as volume current density. That is how you initially think, or you believe that it is to be like that. But however, it is not so. So that is where you have to be very careful. If you ask the question, what are the dimensions of the volume current density, the answer is ampere per meter square for volume. For volume, it is meter square. And in the case of the surface current density, the dimensions are ampere per meter. And in the case of the wire, namely what you call the current in the wire, it's only ampere. Okay, so this is going to be contrasting to what is there in the case of the electrostatics. In the case of the electrostatic, it is not like that. Charge divided by length, charge divided by area, charge divided by volume. So that was quite comfortable. Now it is not like that. Current divided by volume, no. Current divided by area is the correct. And then if you reduce one more dimension, current divided by length. And then in the one dimension, you simply have the current. That means ampere. So therefore, these are some of the points that you should refresh your memory. Of course, these are the basic things that you must have already studied in your BSc. And then the corresponding what is known as the charge conservation law expressed as the continuity equation. Because when you have the charge density and current density, then these two things are related. So the relation between charge density and current density is what is known as the continuity equation. So of course, this is also familiar to you from your BSc work, and essentially the statement is quite simple. The divergence of the current density is equal to the negative of the time derivative of charge density. That is a statement, and exactly it tells you that charges are not allowed to create, or charges are not allowed to destroy. That means whatever charge is there in one place, that charge only should go to another place. That is the reason for the negative sign on the right hand side. So these are the basic requirements. Okay, if you are not familiar with this, you'll have to refresh your BSc magnetostatics part. And then with this kind of basic introduction, we will go to the board and then see how to start writing down the Biot-Savart law, and then perform some vector calculus operation, which means that basically it is going to be a mathematical operation. And finally, our objective is to understand the magnetic field in terms of some other quantity. And that some other quantity is what we are going to call by the name magnetic vector potential. So that is the story about the today's classwork. So for let me go to the board and then show. So first of all, I would like to write down the electric field, because that is the expression which you are familiar with. Namely, the Coulomb's law I am going to write down in the integral form. And once you have this, we are going to write down a similar expression for the magnetic field, namely the Biot-Savart law. So now the constant is mu naught by 4 pi. And then of course the other things like integration will be over the d omega prime. And then here you have a cross product. So the point to be noted is that here, I think the cursor is not coming right. So let me bring the cursor. Okay. So what is the difference between the electric field expression that you have written here And the magnetic field expression that is written here, namely the Biot-Savart law, is the following. You need a charge density rho in order to create an electric field. You need a current density in order to create a magnetic field. That is fine. And then you have the respective units are there in order to take care of the overall units. And remember that these units are valid in the SI system. If you are going to consider the Gaussian system or CGS, then these constants are going to be different. So that is clear. And interestingly, both of them decay like 1 over r square. So both of the electric field and magnetic field, both of them behave like 1 over r square. So that means with respect to the distance, if you far away, if you move, then the magnetic field will decrease like 1 over r square. So that is the second point. And the third common point is that both of them are vector quantities. So therefore, what happens is that you have a vector quantity. Everything is common here. Field is also a vector quantity, r by r square. Everything remains the same. The only difference between the case of the electrostatics and magnetostatics is that the source term is a scalar quantity. Here the charge density is scalar. So that is the point to be noted, that this being a scalar quantity, you don't require any kind of special product. It is a simple multiplication. But here what happens is that the current density happens to be a vector quantity. Why it is a vector quantity? Because current is flowing in a particular direction. Now since current is flowing in a particular direction, that will be the direction of the current, and therefore naturally this happens to be a vector quantity. Whereas charge doesn't have, a single electron is present in one place means you don't have the direction for that. So that is the reason. So naturally what is the trouble is that if these two are vector quantities, you have an r by r square, so there is a unit vector there, and this is also a vector quantity. So I have two vector quantities there, and that is the reason why we have to keep this particular cross product. In fact, I am writing like this. So when I am writing like this, the integration is over omega prime. That here the question comes whether do you want to have a simple multiplication? Not possible. You can have a dot product, of course, but if you put a dot product, what happens is the magnetic field will become a scalar. So your experiment doesn't agree for that, because you already have some experimental evidence, right? So essentially you are going to write down some expression, what we are going to call it by the Biot-Savart law. That expression should agree, or it should be in agreement with all possible experiments that people have performed with the current carrying wire. So because of the nature of the vector, that means the vector nature of the magnetic field, the only option is that you should have a cross product. Then only this final thing can be. That is why I am writing a cross product at the end, so that there is nothing like you don't have to memorize it. So in a way they look very similar, mathematically speaking, and because of this additional vector that is coming into picture, the respective product rule will change, because vector calculus basically involves some kind of theorems like Gauss divergence theorem, Stokes theorem, Green's theorem, Helmholtz theorem, etc. A few of these theorem together with a few product rules, maybe something like 15 product rules roughly. Okay, you don't require all of them. If you know some selected product rules, then you can simplify this. You don't require all of them, by the way. So therefore today's job now is that we will see how to manipulate this expression that we have here in order to understand the nature of the magnetic field. So nature of the magnetic field means what do you mean by that? So that means we are talking about the divergence and curl. So that means you already know the geometric interpretation of divergence and curl. Whether curling means some kind of swirl action, rotating, some kind of rotating action is there, means curling action, and diverging means it has to like when you switch on the light, the light is propagating in all possible directions away from the source. That is called diverging. So do you have diverging property, or do you have rotating or curling nature? Whether do you have such kind of nature, that will be known from the vector calculus. So naturally it provides, because vector calculus provides a lot of geometrical information, and that is the reason why you want to do some calculation on this. So now what you want to do is that we need to know some of the relations which we have already established. So probably I will write down here quickly. So one of the relations is that you have the gradient of 1 over script r, and then the standard notations, there is no need to explain what is script r, what is r prime. All these things are very standard. In the last 10 lectures we have been using them. Therefore there is nothing special to explain for r and r prime. So what is this primed variable? Everything is explained in the previous lectures. So at least I will tell you where we have derived them, so that it is easy to pinpoint. If you have written down in your note, it's fine, but let me at least finish this and then write down in which lecture you can find them. So the first relation you can find it in lecture number 4, and then you have a similar, and then we will be, let us see what happens to the del prime. This we can find it in lecture number 11. Okay, so that is the time roughly. Yeah, you can always find out somewhere inside the lecture number 11. But if you want some kind of time, etc., something like 40 minutes, you go to near to 40 minutes, you will find the answer. And similarly, if you want the other one, the lecture 4 is nearly at about 1 hour. So I'll write down that lecture number 04 somewhere near 1 hour 4 minutes. And this is also approximately same time, because they are same lecture, right? Near to 1 hour you verify. So if you have written down everything in your notes, then there is no trouble. But in case if you want to again search the relations, then these are the references. Okay, once this is clear, now let us start applying some of the rules of the vector calculus. So which rule is now first of all required is that, let us see that our purpose is to understand the divergence and curl. Keep that in mind. Okay, we are interested to calculate the divergence and the curl of the magnetic field. So let me give some equation number. Equation number 1, let us say. Okay, now let us use the product rule, namely curl of the FA. See, curl of a scalar multiplied by a vector. So that should be clear. I mean, what is F and what is A? If you want clarity, I will write down F is any scalar, not a number, but it is a variable. Okay, and A is a standard vector, 3-dimensional in general, 3 or 2, whatever it is, but maximum is 3 dimension. So the expression is given by the scalar multiplied by, so I will write down that this is scalar multiplied by the curl of the vector, then minus the vector, then take a cross product with the gradient of scalar. So this is not difficult. Of course, if you know another expression, it will be easy. So I will write down for convenience a similar expression for divergence. So F times divergence of A. Then you have a plus F times, this time this is just a, what do you call, the scalar product. Okay, so there is nothing special there because it's an ordinary multiplication. So you know which is scalar and which is vector. So then you have a plus. This is important. Now it is plus. Then you write down A dot gradient of F. So these two formulas I am writing down side by side so that you can see the similarity. And only thing you have to note down is there is a minus there and there is a plus there. So that is the difference. And once you have this kind of small difference, then you know both the formulas you can remember easily. And let us say that this is the product rule 1, and the next one let us call it by the name product rule 2. So let us use one of these rules repeatedly whenever required. So now let us consider the product rule 1. Now what you do is that we are going to compare. How can we apply the product rule 1? That question comes. So what you do is directly compare this with the Biot-Savart law. So if you compare which quantity can be related to which quantity, that is what I am trying to explain. So if you want to consider the capital J as capital A, you can give the connection. If these two are equal, then what can you say about the gradient of F? So you'll have to compare. If it is the case, then what will happen to this R by R square? That is what I am trying to explain. So the R by R square has to be brought it from that expression, and therefore what should be F? So what should be f? That is a question by comparing. The answer is that f should be equal to 1 over r. So that is there, right? See that f whatever is there is 1 over r. So this is the idea that we are going to do. That means we are going to make a comparison between the product rule and then the Biot-Savart law. So the term, this particular second term is identically looking like this. So therefore, let us say that this is A, but you don't have directly r by r square here, but instead of that, gradient of f is there. So first of all, we identify r by r square is that quantity, but this quantity is nothing but you can of course put a minus here, and r by r square is equal to the gradient of 1 over r. So now compare the gradient here. So this gradient is this gradient that is there here, and therefore this f should be equal to that 1 over r. And this minus can also be brought. There is no problem. You can always put the minus and then attach a minus and then make this plus. So that is what is the algebra that we are going to do. So in that case, what happens? So remember what are the mappings that we are going to do, and therefore let us use the product rule and then rewrite the Biot-Savart law. So then we will be writing B of r is given by mu naught divided by 4 pi. Then the integral, you have the j of r prime vector, then cross the gradient of 1 over r. So that is the same expression I have written for convenience. And now we are going to say that the minus let us bring in now. So I have written minus that. So that minus is clear. From where you got the minus? So it is there. So that minus only I have written there. Okay, that minus is what is coming here. So once that is clear, then we are ready to apply the product rule 1. Then B of r is equal to minus mu naught divided by 4 pi. So now you write down the two terms. The two terms should be there, right, in the product rule. So the first term I will write down del cross. So you have j of r divided by script r. For convenience, I will write script r. Bracket is not good. Okay, then we have a minus. You should remember what is the term that was there, so that it will be easy. And every time going back and coming is very difficult. So if you have it, if you are writing in the note, it will be easy. And then that's all. Two terms are over. Close the bracket. d omega prime. And what is the point to be noted is that I have written the script r so that I can avoid every time writing r minus r prime. So that is the thing. So whenever required, we will use r minus r prime. But remember that the script r is nothing but the modulus of the r minus r prime. So once that is clear, now we will see what will happen to the minus sign there. We already put a minus and therefore this becomes plus. Okay, so now what is interesting is that there is an interesting thing going on in the second term. That's what I'm writing. I would like to say that each one of these terms is a function of different variables. So del is a function of x, y, z means, so what is the meaning of that? Del means what? Del means I times dou by dou x. Therefore x is there. Then plus j times dou by dou y. So y is there. But however, in the case of the j, what is j? J means current density. So you see here, whenever you write j, j is a function of r prime. Isn't it? So the diagram that we are using now throughout the electrodynamics course from day 1, the primed variable corresponded to the place where the sources are present. Now the source is current density. Therefore, if you say current density is a function of r prime. R prime means x prime, y prime, z prime. Because you know what is r vector, right? R vector is xi plus y times j plus z times k. That is how you write r. So that is what I mean to say. So therefore, this is a function of x prime, y prime, z prime. So ultimately what is happening, you see that this is a differential operator. Ultimately it is a d by dx, that's all. So d by dx is one dimension. So you are performing d by dx of some function of x prime. So how much is that? Isn't it? So similarly, you will be having d by dy of some function of x prime, y prime, z prime. That means that these variables, these x, y, z variable is not at all there here. And therefore, if you perform a differential operator, what answer will you get? You are supposed to get 0, right? D by dx of x prime, y prime, z prime, whatever is there, finally it is going to be 0. So that is what I said, that this is interesting, and therefore I'll make a conclusion that this entire second term goes to 0. And therefore you are left out with the first term alone, and therefore it is easy to simplify. So our conclusion is, therefore, let me write down only the first term. So you have the integration of the entire expression mu naught by 4 pi. You have a del cross, then you have a j by r. Whether you write j of r prime or j by script r, it's all fine. The only thing what is clear here is that j means j of r prime. So remember, sometimes we write j, sometimes we write j of r prime. But whether you write whichever style, it is ultimately the meaning is j is a function of r prime. So that should be clear. Only for convenience, we will write like this so that, opening bracket, r prime, everything need not come here. So it looks a little bit comfortable, or it looks a little bit elegant when compared to this. That's the reason why we write. But ultimately j is a function of r prime, so that will not change. So now what we will do is, in order to make certain things clear, I would like to rewrite this script r so that it is actually the modulus of the r minus r prime, so that we can make some conclusion based on that. That's what I'm going to write down in the next step. So mu naught divided by 4 pi is anyway a constant. I'll bring it outside. And there is some interesting point that I want to explain so that you can rewrite this expression. The point is that I would like to bring the del operator first of all and put the integral operator later. You see, I'm interchanging, that I will explain now. Once you interchange, the rest of the thing is same. Now I will write down modulus of r minus r prime. And of course, the integral region is d omega prime. And that's all. You close the bracket. So the point is that it's very clear that this integral operator has been taken first, and then the integral operator is taken second. You see that's what happened here. What is the difference between these two? That is the only difference. D omega prime is there here, no change. This script r is only this one. So script r also nothing happened. It's only rewritten in a appropriate expression. And j is nothing but j of r prime. Both are same. Then what is the change now is that the integral operator has come here. That means it has come later, and the first operator has been delta. So the what you call the del operator has been taken in the beginning, which means that ultimately what happened is that the two operators, namely the differential operator and the integral operator, their positions got exchanged. Positions got exchanged means, what do you mean? What do you mean? Let us understand first of all. In this expression, okay, in this particular expression, you have to perform the differential operator first of all. That's the meaning. You have to finish the differential operator. That means you have to finish the curl. After finishing, then only you have to perform the integration. That is the meaning. But if you write like this, what is the meaning is, first of all, you have to finish the integration with respect to the omega prime variable. After performing the integration, now you have to perform the differential operator. That is the meaning. So naturally the question comes, can you change the order of integral like this? Okay, performing the differential first and then integral second, whether that is equivalent to, can you perform the first of all integration and finally differentiation? Can you do that? That is the question that comes. It cannot be done always. But now something is special, and therefore we can do. What is special here? That's what I would like to write down. First of all, I will write down so that it will be easy. So why we are able to do this kind of interchanging is because the del operates only on xyz variable, whereas the integral operator operates on x prime, y prime, z prime. And of course, d omega prime means all primed variable that you know. And therefore, ultimately what happens is, so this is the point that you'll have to remember. Whether you write this way or d cube of r, they are all identically same. Whatever way you write here, that's fine. The point to be noted is that the integral operator, that means this one, is with respect to the primed coordinate. That is why I say x prime, y prime, z prime. Differential operator will be operate only on x, y, z. That means del operator will not touch x prime variable. Del operator will not disturb y prime variable. Similarly, the del operator will not disturb the z prime variable. That means if at all such variables are there, they will be treated as constant. That is the meaning of partial derivative, right? Del operator means what? Dou by dou x is there, dou by dou y is there. So when they are partial derivative with respect to x, x prime is a constant. And therefore, ultimately, what is the meaning that you get? The meaning is that the del operator and the integral operator, they operate independently. Independently means one will not disturb the other. The integration will not disturb the x, y, z. The del operator will not disturb x prime, y prime, z prime. So they will perform their mathematical operation within their limits. Integral will not disturb differentiation and derivative will not disturb integration. In this case, not general, okay? In this case, I am telling. In our case, this is the story. And because of that reason, we have the freedom of interchanging the two operators. This is very crucial. We are going to use this idea as many number of times as you want. You can always interchange them because it is very visible directly. Where is visible is that when you put the integral here, you have a d omega prime. So automatically that is the meaning. So similarly, when you put a prime here, you have omega prime. So integral will be operating only on the primed variable. That's very clear. And remember that delta, whatever that you have written, the del operator, we don't have a prime. If you have a del prime, then the story is different. If you have a del prime here, then it will operate on x prime, y prime, z prime. Okay, that point you keep in mind. And once this is clear, we are going to give a name for the integral. Okay, so I would like to write down the whatever integral that is going to appear here. I would like to highlight. Let me show that. So in this expression for the magnetic field, there is an integral looking like there is an integral appearing inside. So that quantity, let me highlight, and then we will give a name for that. So only that integral quantity is the integral quantity is a vector or scalar that you know, right? So if you evaluate the integral, it is supposed to be a vector. So this quantity, we will call it by a name. And the integral after evaluation, it is supposed to be a vector. Okay. So that point I will write down. And we will call this quantity by the symbol capital A vector. We can give any symbol, but traditionally, capital A vector is the name that is given for this. And in this particular case, what do you mean by that is that, what do you mean by this saying that we will call it? That means we are defining. We are going to call it by the name means we are going to define that the capital A vector is given by the integral of whatever is there, the same thing you write down, j of r prime d omega prime, then divided by modulus of r minus r prime. And that's all. So once you are going to give this kind of name or this kind of, once you are going to give this kind of definition for this, then the equation for the B is going to be looking very simple. So I will write down that is equal to mu naught by, so where is the constant? So that constant we will let us write down, we will have a mu naught by 4 pi. Constant I want to write down, then only the del operator will come. So mu naught by 4 pi, then what is left out is now we can write del cross A. And that's all. So this is the expression that looks reasonably simple, so that all the integral has been defined into the capital A. This expression, we prefer this expression so that it is easy to understand and remember. And there is a point to be noted, so I would like to explain here. Now, when you are writing the BFR here, you have a mu naught by 4 pi, and then you have the del cross A. So it is completely optional to put the mu naught by 4 pi into this definition. See, you just imagine what will happen if you transfer this constant here. You can always put it. So A of r can be defined as mu naught by 4 pi into this integral. If you transfer this constant here, then here no constants will be there. You can simply say that B of r is given by curl of A. You have that freedom. We will do that. We will do that in the at the end. Okay. So let us have this constant right now. After finishing all the calculation, let us transfer. We will transfer this constant inside the definition for the capital A, so that mu naught by 4 pi will come here, and that mu naught by 4 pi can be eliminated here or removed here. Okay, that we will do at the end. For the time being, let it be here. So what is the meaning of this kind of equation? That the meaning is that magnetic field can be understood. We can understand the magnetic field from another vector quantity. From another vector quantity, we can say that, okay, A vector, and we can give some name for that. Of course, we are not given any name. So later we are going to give the name. So let me therefore write down. So which we can call by the name magnetic vector potential. So I will explain why the name has come like that. Okay, instead of saying always capital A vector, better to give the name. The name is magnetic vector potential. I'll explain why the wording has been given like that. Later I will explain, maybe in the next class. But now this is how we are going to consider the capital A, and let us have the equation number 3, which means that the equation 2 should be there here. So this is the first point. The first point means that after doing a little bit work with the vector calculus, our conclusion is that magnetic field can be understood in terms of another quantity. That's the conclusion. Okay. So once this is there, let us now try to evaluate some more quantity. I mean the divergence and curl, for example. So let us try to evaluate what is the divergence of the magnetic field. Because we are having the equation 3, which is the latest equation. Now remember, equation 3, by the way, is what? Your Biot-Savart rewritten in a different style. That's all about it. So therefore, let us do the divergence now. So divergence of the magnetic field is equal to the divergence of. So write down whatever is there in equation number 3. That's all. I'm simply copying it. That's all about it. And then now you have divergence is there. You have a curl is also there, isn't it? So this is the divergence of curl of A. So now you need some of the product rule. There are several product rules are there in vector calculus. That is a point to be noted. So what is the expression for the divergence of curl? Of course, this is the quite simple thing, namely it's 0. It's always 0. That's all. That is interesting. For any vector, it is 0, and therefore our conclusion is that the divergence of B equal to 0 always. So remember, the word always is coming from vector calculus. Okay. So as long as you have vector valued function, for every vector valued function, divergence of curl is 0. And therefore you have to write down this expression always. So this is the most important and striking feature of the magnetic field. So what is visible from this particular equation? Okay. So what is visible from this equation is the nature of the magnetic field. What is this nature is that it doesn't have divergence. This is to be contrasted. See, you have to write down on a side-by-side basis. If you write down what is the divergence of electric field here, you will realize that the divergence of electric field is given by rho by epsilon naught. That means the right side of the divergence of the electric field is not 0. And therefore, by making a comparison like that, you can make a conclusion that similar to the charge density in electric field, you don't have anything in magnetic field. Isn't it? Divergence of B is 0. 0 is right side. What is there for electric field? If you write an equation here, how it look like? Divergence of electric field equal to rho by epsilon naught. So right side is rho. Rho means charge density. So similar to charge density, you don't have anything here in this equation. So this mathematics, namely this vector calculus, gives you the information that magnetic monopoles are not there. Monopole means single charge. You have electric charge, right? Electric charge means a plus q is enough or a minus q is enough. You don't require them in combination. You don't require plus q and minus q together, not required. Only 1 plus q or only 1 minus q is sufficient to generate the electric field. That is the meaning. Here, 0 is there. 0 is there means such kind of monopoles. Remember the word why monopole comes? A single charge. A single north pole, a single south pole, such a thing doesn't exist. That is the meaning of the 0. If it is existing, probably that should have come here. Mathematics should have given the information. But since 0 is there on the right hand side, we now interpret, or we say that we understand the magnetic field. How do you understand the magnetic field? Is that it is the one generated only by dipoles. That is the conclusion. There doesn't exist monopole. What monopole means? Magnetic monopole. Magnetic monopoles doesn't exist. So that is how we interpret and understand the magnetism theoretically. So you understand how we are performing the analysis. So how the vector calculus or how the mathematics is going to help you understand the behavior of the physical system. So this is how you understand and reinterpret, or we say interpret. So this is the first point. Second point is that the divergence of B equal to 0 means it doesn't diverge out. If you want to plot the contours, the magnetic field lines doesn't start from one place and then diverge away. That doesn't happen. But instead magnetic field lines are closed, because that can be done quite experimentally. You can do it. Uh, right from the bar magnet, you know already, right? It starts from the north pole and then go around and then join in the south pole. And once it joins in the south pole, again it comes back inside the magnet, and then what you call the magnetic reconnection takes place, and once again it's a closed loop. So ultimately magnetic field lines are closed. So that is the information you gain from the divergence of B equal to 0. So this is how we understand, or we perform the physical interpretation for this equation. So once this is clear, we are ready to evaluate the curl of the magnetic field. So let me therefore, I think the space is not there. I'll move on to a different place. So we are interested now to evaluate the curl of the magnetic field. So which means that the same expression that we have, equation number 3, we will write down, and then only use the different product rule now. That's all about it. So I write down mu naught by 4 pi, then you have a curl of, then you have a curl of A. So curl of A is the expression for the B. So remember equation 3, then it will be fine. Okay, if you don't remember, I'll write down the equation 3 here. Mu naught by 4 pi into curl of A. So that was your equation number 3. So keeping that, now we can easily verify how this is coming. And now we need curl of curl. So two curls are coming. So let us open a book on vector calculus and then write down what is the formula for curl of curl. It is given by the gradient of divergence minus the Laplacian. So like this you read curl of the curl equal to gradient of divergence minus the Laplacian. So if you want to write in terms of equation, it looks like this. Gradient of divergence minus Laplacian is del square. Okay. So sometimes, reading in terms of curl grade is sometimes easier. So that is why I'm reading like that. So once this is clear, let us substitute that now. So I will write down the gradient of the divergence of the capital A vector. Then you have the minus of the Laplacian of the capital A vector. And that's all. But then you should remember what is capital A. Capital A is the magnetic vector potential. So keep that for your reference. So if it is the case, let us substitute this capital A, then how the equation will look like. So curl of the B vector is, let us substitute, the equation will look with integral etc. That's fine. It may look a little lengthy, but it's fine. Let us write down carefully. You have opened the bracket, then write down the gradient operator, then open a big bracket. Okay, now there's a divergence, so divergence is fine. Now capital A is an integration, right? So put the integral. The entire thing you copy. So whatever is there in equation 2, right? Simply copy it here. And that's all. So that is the expression first term. Close the bracket, close the square bracket. So first term is over. Then second term is minus. Then you have a del square. So anyway, we are multiplying the mu naught by 4 pi every term. Okay, del square of the same expression. Once again, copy the equation number 2. So the expression looks a little lengthy, but it's fine. We can easily manage. Okay, so therefore, you have to now understand and then rearrange the order of differentiation and integration. So once again, we are going to use the same trick here. So I will write down the trick you already know, right? The del operator operates on x, y, z. Integral operates on x prime, y prime, z prime. So that is the idea. So we can always interchange the differential and integral operator. That is what I am writing down, which is already explained to you. That is the idea. Now that we are having two integrals, I would like to let us evaluate separately. I'll put some color for both of them. So the first one is the first integral I1. Let us consider the green color one as the second integral. We can deal with them separately and then we'll combine later. So let me therefore write down the first integral like that. It is the same thing where I am interchanging the order of operator. Okay, gradient you first of all write down. Now I am interchanging the order. So first of all, I'll put the integration. Afterwards, I'll put the divergence. So now the order is interchanged. That's all about it. The remaining things are going to be same. So I'll simply write down something like 1 over r. Okay, you can write down 1 by r minus r prime. But okay, I will write down 1 by script r so that it will be comfortable. So you have to be careful. The divergence is up to that. Okay. Then you have d omega prime. And then the big bracket you have to close. That's all. So that completes the pink color, first integral. And now we are ready to perform the integration. And you know what we have done. We have simply used the script r. That is first thing. Second thing, what we have done, that the del operator and the integral got exchanged. We have exchanged it. So these are the points that you note down. And now once we have an expression like this, now you have to search your product rule. I said that there are more than 10 product rules are there. So you have to search which product rule will fit for this equation. So for that, what we will do is let us identify some vector and some scalar here. So do you have a scalar? Do you have a vector? That is what we are going to identify. Yes, there is a vector. We will say that capital F here, and there is a scalar. We will call it by k. So therefore, if this is the situation, then how the integral itself looks like? That is the point to be noted. If it is the case, it looks like some standard rule in vector calculus. So the integral looks like this. I will write down. The integral is looking like integral of the divergence of k times f. That is some scalar times f d omega. That's all. That is how the integral is essentially looking like. So as you can see, this is their divergence. K times f or f times k, no change. It's only scalar multiplication. So 1 by r can be the first term or second term. That doesn't matter. So now what all you have to do is that you'll have to find out what is the corresponding product rule for this kind of expression. So I think I will express this equation separately in another place and simplify and then come back here. Okay, otherwise this board itself will be clumsy, scattered with many other different topics. So let us discuss about the product rule separately in another rough board or say rough paper. Then once we understand that, we will come back here. So that is the idea. And we will use the Gauss divergence theorem for now. Okay, I'll go to the rough paper or some other place. So the standard Gauss divergence theorem, you first of all write down. It is the divergence of the vector, then volume integral. That will be equal to the surface integral of the normal component. Normal component means v dot ds. That's all. This is the standard expression. Now what is that we want to do is that we want to replace v by k times f, because just now we have seen that some k is there, some f is there. So there is no confusion here in the sense that every vector can be written as some scalar times some other vector. It's possible, right? You can always find some vector. If you take some scalar out, and then the remaining thing will be that. You can write like this. And therefore, you are going to substitute k times f in this place. Similarly, in this place, you are going to substitute. So if you do that, how it is going to look like? Simply you write down the k times f, and the rest of the thing is same. So this is how the Gauss divergence theorem is going to look like, and we have identified what is that we have identified is 1 by r, and also the what you call the magnetic vector potential, and then capital, I think it is capital J, right? Not magnetic vector potential. Okay. So whatever we identified, in the expression, that we are going to substitute now. So k is nothing but 1 over r. So you put a 1 over r here. Then capital F is capital J. So that would be equal to the closed surface integral of j dot j of r prime dot ds divided by script r. So of course script r is a scalar that is there. Now we are going to understand, or we are going to interpret what is the meaning of this. So the first point that you understand is that capital J is supposed to be the current density. So I'll write down, better I will write down instead of current density. And important point, as I explained in the very beginning, the units are ampere per meter square. Okay. And then ds prime is as usual, the elemental surface area, and dimensions are as usual, meter square. So therefore, if it is the case, what is the meaning of j dot ds? So you have a j dot ds. So the meaning of the j dot ds is that it is the current flowing perpendicular to the surface, or we say normal to the surface, whatever name. Okay. So the dot product represent normal component. That is the standard terminology, or that is the geometrical interpretation. Whenever you have a dot product, it is known as normal component. That is why we say that it is a current flowing perpendicular to the surface. So that means whenever you are going to have an integration like that, that integral is a closed integral. So you are going to use all this information to consider what will happen to the integral. So you are going to perform a closed loop integration. In that closed loop, current is flowing. That's all about. You have a closed loop, current is flowing. So you can imagine this kind of situation with the one in your circuit theory. Namely, when you have a circuit, and if you are going to consider the total current flowing in a closed circuit, then what will be the expression that you try to write down that. So the expression is looking like algebraic sum of currents in a closed loop. So you know that algebraic sum should be 0, because we are closing the loop, right? If it is open loop, then it is not 0. So because it is closed loop here, the of course you talk about the algebraic sum, I am writing like that in the case of discrete circuit element. But here we are performing the integration because you are considering small elemental elemental surface. So the sum will become the integration. So that is quite trivial. So in the case of the discrete electronic circuit, you can even perform the summation. And here you have continuous distribution, and therefore you are performing the integration. So that difference, there is no trouble. So the point to be noted is that the quantity is going to 0. So that is what we mean to say, and therefore this integral is going to 0. That is a point to be noted. So this is one of the crucial points that enters into the picture in our calculation. And there is a point to be noted. So I'd like to mention this point, and then we can move ahead to the calculation. Now here there is a important point is that whenever you are considering the algebraic sum of currents, then that particular total current is going to 0. That is generally true when the currents are steady. That means when you have a uniform current, then this is generally true. But you can imagine what will happen if you are going to have fluctuating current density or fluctuating current. So in fluctuating currents are there, what happens is you don't have to worry about the mathematics now, because already some physical input is available. You know physically, that means somebody has discovered, right? When there is time variation of the current densities are there in a circuit, what will happen? You remember the Faraday's law, right? So therefore Faraday's law will enter into picture when you are having a fluctuating current density in a circuit. So therefore the point to be noted is that when you are making a 0 here, we are making an assumption that the steady current is flowing into the system. Steady current is flowing into the system means the charge density that is moving, right? The charge density which is moving, that should not change with time. That is the meaning. So therefore indirectly, where there is an assumption going on here while writing 0, namely that the J is uniform current density. That is important. So uniform current density is flowing in the volume here, in this particular volume. Then the corresponding surface, you will be having this expression, current density. So therefore, because of that reason now, for the static situation, we will make it 0. And therefore, once this is clear, we will go back to our original board and then say that this particular expression is 0. Of course, for the as I explained, this 0 is not valid when you are going to have dynamic situation. Okay, only for uniform current or steady current, this is agreeable, acceptable. Okay, now let us come to the second integral. Let us copy the green color integral. So the I2, okay, so the I2 I have simply written down whatever was there in the green color, and we will use the same method, namely that the differential operator and the integral operator we are planning to exchange. That means the order will be exchanged, and not only that, we will also use the del square of 1 over r, because the Laplacian is there, right? So del square of 1 over r is nothing but minus 4 pi times delta cube function. I mean delta function. So here delta cube, whether you write delta cube or delta, that doesn't matter. It's all the same. How do you know that the 3 comes here is because r is a vector. See, when you are considering vector quantity here, if you are considering 3-dimensional vector, the delta will be delta power 3. If we are going to consider 2-dimensional vector, then this will be delta to the power 2. Okay, if it is a 1-dimensional case, then you simply write down delta of x. So that 3 is not very important. Even if you don't write 3, no problem, because vector will clearly indicate whether 3-dimensional delta or 2-dimensional delta. That clarity will come. So the delta to the power 3 is not compulsory. Even if you write without 3 also, it's fine. So okay, so these are the information that are required. Now let us substitute that now here. So I will write down the first of all, I will write down the integral. I will put the first of all, and then put the del square as a second operator. So now I will put the del square operator of. So inside the bracket you can put a 1 over script r. Then you have a d omega prime. Of course, you can ask the question why the delta square will not operate here, because see this integral is going to come like this, right? You are going to pull the integral outside and then push the del square inside. That's what you are going to do in this exchange process. That is fine. The question is why del square is not operating here. That also is the same reason. Del square whether it is operating or doesn't operate, there is no effect, because as usual, what is del square? Del square means dou square by dou x square plus dou square by dou y square. That means this Laplacian operator will be affecting only x, y, z variable. But what is there here? The current density is a function of x prime, y prime, z prime, and therefore the partial derivatives appearing in the Laplacian will not affect it, which means that we can take outside. That is the meaning, right? Whenever something is not affecting, it is like constant only, so you can bring outside the operator. That's what happened here. So when you are pushing the del square inside, anyway j will not be affected, so let it be outside. Then who is left out after removing this j of r is only 1 divided by script r. That's what we have written. And now that we have the del square of the 1 over r, we can now use this kind of an expression. And in fact, I already explained, or I already mentioned in which lecture number you can we have done the proof actually, so you can find out from that lecture if you are not comfortable with this. So now we are going to substitute this expression here and then proceed with the integration. So let me therefore substitute now. So the point that I explained is this: the capital J is independent of x comma y comma z. So that is the reason why the J of r has come outside the Laplacian operator. That's what I explained. And now let us come back here and then substitute. So that is equal to mu naught divided by 4 pi times the integral. For simplicity, let us write down simply j here. So j vector, then you have a simple, this is a simple multiplication. Then you have minus 4 pi, the delta function r minus r prime into a d omega prime. So that's what it is. And of course, you should remember that, the del square is a scalar operator. 1 over r is also scalar. So everything is scalar here. So therefore, this 4 pi delta cube, all are scalar quantities. And this dot is actually a scalar multiplication. So there is nothing like vector multiplication here. It's an ordinary multiplication. That's all about it. And once you understand that this 4 pi is getting cancelled here, then what is left out is minus mu naught times the integral over the omega prime. You have j times the delta function. So j times delta function, that's all about it. And now you should be able to recognize how to evaluate this integral. So minus mu 0 times, if you evaluate the integral, you simply get j. That's all. So this should be clear to you, because we have already learned how to evaluate the integrals of the delta function. So if you are not comfortable with that, you will have to refer to the previous lecture. So I will write down that for the Dirac delta function, for this kind of integration, see our previous lecture. I think it is lecture number 3. So I'll write down. You have to verify lecture number 3 at some time like 43 minutes. So you just search there. Exactly this kind of integral will be there. So you'll be able to see that the effect of the integration will give you only the j. So essentially, you forget about all mathematics. You can easily understand like this. Whenever r equal to r prime, that means at a particular place, what is the condition given by r equal to r prime? At that place, current density is present. That's the meaning. And whenever r is not equal to r prime, you don't have current density. That means you don't have current. So this delta cube, or we say that the 3-dimensional delta function, exactly tells you, or it precisely tells you, where current is present and where current is not present. That's all it tells. And therefore, this particular this kind of the integral will tell you the total current density present in the system. So remember, each one of them is a current density. So it is like switching on and switching off. The delta function will switch on. When it says that switch on, that current density will come here. And then it will tell that the current density will switch off when r is not equal to r prime, and therefore 0 will come here. So which means that plus 0. So like that, all the small current densities wherever present inside this big volume will be added up here, or we say that this is the total current density that was present in the system. So this is how the meaning comes. Of course, the more details are there in this lecture. So that is a point to be noted. And now that we have completed this integration, we are now ready to assemble both the integration and write down what is I1 plus I2. So now the point is whether it is I1 plus I2 or not. So let us verify. Is it plus or minus? So that is the one I want to tell. So there is a minus is there, right? So that is important, not I1 plus I2. So that is I1 minus I2. So keeping that, let us write down what is our final conclusion. So finally, what is that we are evaluating? We are evaluating the curl of the magnetic field, and that is given by I1 minus I2. And therefore you can now verify that this is equal to, the minus is gone there because that minus is cancelling with this, and then you get a mu naught into J. So this is a very important conclusion, but remember that this important conclusion is valid only for magnetostatics, as I already explained to you why it is so. Because we have used some reasoning, right? We have assumed that uniform current density is present in a circuit kind of thing, so that you made that integral 0. That is the reason. So therefore, that point I would like to write down. But let me first finish this one. So how do you know that this is valid only for magnetostatics? Is that it is lying inside I1 equal to 0. So if you see the integration that we have done, and then we explained that the algebraic sum of the current is 0, all these things. So at that time we have made an assumption. That it is supposed to be steady current. Then for non-steady current, what will happen means Faraday's law will enter into picture, isn't it? So therefore, the any changes will be reflected as the time derivative of the magnetic field. So that is why this integral may not be 0 in the unsteady case. So right now that we will not worry. So at least for the case of the magnetostatics, we are happy to make the integral 0. So that is a point to be noted. So and therefore this information should be reflected in our conclusion. That's what I'm trying to say. So whatever assumption that we made here, that should be reflected in our conclusion, namely the validity on the steady currents only. So that is the point. And so keeping this as the important point, that the curl of the B is given by mu naught into J is valid only for magnetostatics. Okay, so what was the earlier conclusion we got is divergence of B equals 0, but I am writing this because here the condition is always. So I am just writing down the previous conclusion in order to make the contrast. The contrast is, where for the curl you have the validity condition, for the divergence no validity condition, it is always valid. So this is interesting. And then what was the very beginning we got the conclusion is that the curl of A is the B, and now I will put the constant here. So I said that we will put the constant to the A. Now we have done that. So you got the point. So here we were using the mu naught by 4 pi here. That was the case. So it is optional. We can put the constant here or here. So now we have thrown the constant mu naught by 4 pi into inside the definition for the A vector, so that this equation looks much more compact. It looks simple. B equal to curl of A. So this is how the understanding has taken place. So we have started with the Biot-Savart law, and then first of all we established this. After that we established this. Then finally we have proved this. So this is how it has come. And now I am just making a summary of all the conclusions. And therefore the final conclusion would be that we would like to keep the constants inside the capital A vector, so that here it looks very neat. That the magnetic field can be written down as the curl of the A. So our conclusion therefore is that we are going to call this by the name vector magnetic potential. So let it be that be the conclusion, and in the next class I will explain why it is given the name potential, and then we will try to explore more about the nature of the magnetic vector potential. Okay, so there are some points to be noted about this capital A. So those details we will see in the next class.